It was a revolution to the world to be able to see inside the human body without using a knife. X-rays pass through all materials to some extent and can reveal internal structure. A German physicist, Wilhelm Röntgen, discovered X-rays quite by accident. In 1895, he was investigating how electricity passes through gases. He connected a high voltage across the terminals of a special tube. The gas glowed, but it was too dim to see by daylight, so his laboratory had to be darkened. And one day he saw something quite unexpected. Something else was glowing too. This glow was caused by new and invisible rays coming from his apparatus. Röntgen soon found that these rays could pass through wood, paper, and human flesh, his wife's hand. To take X-ray photographs in hospitals, small and simple tubes were developed. But they needed a lot of other equipment to generate the high voltage to work the tubes. However, no one then realized that a large dose of X-rays can kill human body cells. They often did the patients more harm than good, and the radiographers using the equipment all day were at an even greater risk.
Of course, you were holding the screen in your hands, and we had to be placing things with our hands sometimes while the beam was on, and it wasn't until we learnt what was happening that this was stopped. And of course, the gloves for so-called protection were very primitive and only absorbed a little radiation. The result is that, in fact, I think all the original workers before the First World War had damage done to their hands particularly. And of course, I got some damage to myself, which was done in the very early days, and that is the result. There, you see these warts, scars, and the skin doesn't heal up, it cracks.
They didn't all get off so lightly. A monument in Germany to 359 people who died from overexposure to X-rays. Hidden solids revealed, a fantastic idea to people in the last century, and the cartoonists of the time were quick to see the funny side. Attracted by all the publicity, Henri Becquerel began work on similar lines. And he discovered rays which seemed at first just like X-rays, but were actually given off by certain solid materials. These new rays also affected photographic film. And again, like X-rays, they made air conduct electricity. And this provides another way of detecting them. A high voltage is connected between a metal gauze and a wire just below. When a capsule containing a source of the rays is placed near the apparatus, sparks jump between the gauze and the wire. The Geiger-Müller tube works in much the same way, but is more sensitive. The strength of the radiation is indicated by a loudspeaker and shown on a meter. But Becquerel soon found that his rays were different from X-rays. The magnet appears to stop the rays, but in fact they've only been deflected sideways. X-rays aren't bent by magnets. Becquerel really had discovered a new kind of radiation, one which comes from inside certain natural minerals. The actual source of this radiation interested Marie Curie and her husband Pierre, and it was she who first used the word radioactivity. Their laboratory was little more than a rickety old shed. They spent 4 whole years purifying tons of radioactive ore using little more than pots and pans. They discovered a new element, radium, intensely radioactive. This, the first tiny bit of radium, glowed bright enough to be photographed. These girls worked in a watch factory using one of the first practical applications of radioactivity. They painted luminous watch dials. But they often licked their brushes, and this was dangerous. The radioactive paint collected in their throats and caused tumours. Lord Rutherford made the next big breakthrough. He discovered there were at least two kinds of radioactivity. One sort wouldn't even pass through a sheet of paper. This he called alpha radiation. The other kind would pass through a few millimeters of aluminium before being absorbed. The sheets are held by the corners to avoid the beam. This more penetrating radiation Rutherford called beta rays. A beta ray source and a detector. Exactly how much radiation gets from the source to the detector depends on what it must pass through. This provides a way of measuring how much material is actually being made in a manufacturing process when a sheet is being made continuously. An example is the paper-making industry, where the machinery runs day and night making one long sheet of paper. A source of beta rays and a detector can be used to measure thickness. The thicker the material, the less the radiation that reaches the detector, and so the reading on the meter will vary with the thickness of the sheet. But the density of the material is important too. Aluminium stops only some of the radiation, but exactly the same thickness of lead stops it all. In the paper-making industry, it is the density of the sheet that must be controlled and checked during manufacture. To measure this, there's a box above the paper containing a gas which emits beta rays, and underneath is a detector. The paper passes through the gap. The output of the detector is fed to a meter which shows how much the paper density varies. Too much variation, and the machine is adjusted. In 1900, Paul Villard discovered a third sort of radioactivity, gamma radiation. He found that unlike beta radiation, gamma rays are not deflected by a magnet. Gamma rays have very high energy. They pass easily through several centimeters of lead. The penetrating power of gamma rays means they can be used like X-rays, but because they don't need special tubes and electricity, they have many more applications. In the production of china clay, a powerful water jet eats away the cliff face and carries it into enormous tanks where the clay settles on the bottom. The water and smallest particles of clay which take too long to settle used to be pumped into the rivers and down to the coast. At the Cornish china clay pits, they decided to clean up the rivers. A possible solution was to build a pipeline directly out to sea. To find out how well this would work, they chose to use a radioactive material. They contacted Harwell, the Atomic Energy Authority, one of the few places where substances can be made radioactive. Some glass was ground to a powder and sealed in bottles to be put into the nuclear reactor. The conditions inside a nuclear reactor change the atomic structure of the powder to make it radioactive. When it emerges, the powder must be handled behind thick protective screens. For the journey to Cornwall, it's loaded into a lead container to protect everybody from the gamma radiation. Off the coast of Cornwall, a pipe was lowered at the place where the planned outlet would be. The radioactive powder was unloaded very carefully and put into the pipe. 100 tons of china clay were put into the same pipe and mixed with the radioactive powder. Then all of it was pumped to the seabed. At intervals over the next 5 months, the survey team used a Geiger-Müller tube to find out how the radioactive powder and china clay had spread out. Most of the clay stayed near the dumping place, but some had spread much too far along the coast, so the pipeline wasn't in fact built. The waste disposal problem had to be solved another way. But what about the radioactive material left in the sea? Is it dangerous? Well, it was spread over a large area, and the activity of all radioactive materials dies down. If we feed the output of a Geiger-Müller tube to a graph plotter, we can show the decay of a piece of gold that has been made radioactive. In 40 seconds, the radioactivity of the gold has decayed to less than 1/20th of its original value. All radioactive materials decay in this way, but some, like uranium, take thousands of years instead of a minute or so. A rapid decay is essential in medical uses. To find out if this man's liver is working normally, he's injected with a radioactive solution. The gamma rays pass through his flesh and are then detected by a special camera that shows which parts of his liver are working. Although it's called a gamma camera, it doesn't work like an ordinary one. Only the gamma rays entering at right angles are used to make the picture. A lead block with parallel holes in it cuts out the other rays. Those that get through hit a crystal which gives a flash of light when a gamma ray hits it. Each flash of light is converted by flash detectors into an electric pulse, which is fed to a computer. The computer will display the pulses in the form of a picture. To demonstrate the gamma camera, we can use a plastic box, shaped so it contains varying amounts of radioactive liquid. The pattern of the flashes on the cathode ray tube shows where there's most radioactivity. An ordinary camera takes a picture to give a permanent record. The computer also displays the picture on a television screen. The area of least radioactivity is top right. The greatest is on the left at the bottom. Now the gamma camera is used to show the pattern of radioactivity in the patient's liver.
Now, Mr. Clifford, I want you with your back to the camera, sitting on the couch, if possible. Do you think you can manage that? That's it. Back right up against the couch. Is that about right? To the left. Can we move you down a bit? That's fine. Now if you can stay very still just there, Mr. Clifford.
The television picture is used to help the doctors position the patient. But they also take more normal gamma ray photographs as a record to discuss the tests later in the day.
Well, we can see his liver quite clearly. It looks fairly normal. You can see the right lobe here, little notch between the right and the left lobes of his liver. And also on this front view of his abdomen, you can see a little bit of his spleen showing here. And we see the spleen much more clearly on the back view here. And I think you'd agree, Tony, it's obviously enlarged. And this is confirmed on the lateral view here. It's only moderately enlarged, but it's certainly abnormal.
Fine. The next case is also a liver scan on a Mrs. Williams, and she is a 75-year-old lady, a rather thin lady, who is known to have been a heavy smoker all her life and has developed a lung cancer. Now, she again has been troubled by pain in the region of her liver.
Well, here really the situation's different, isn't it? We've got a very big liver, but I suppose the most marked thing are these areas of diminished radioactivity, which represent holes in her liver, which you can see on the front view, and again on the back view, a very large area of diminished activity in this lobe of her liver. And
the gamma-ray pictures need only a small amount of radioactivity, so the patient isn't harmed. But sometimes we want to kill living cells when they're diseased, and that needs a lot of gamma radiation. For this, radioactive cobalt is used. It's contained in a thick lead box in the head of the machine so that no radiation escapes until it's ready for use. The key is one of the many safety precautions. The position of the machine can't be changed without it, and the same key must be taken outside the treatment area to operate the equipment which unshields the radioactive source. The radiographer will keep the key with her until all the technical staff are outside the treatment area. The radiographers check that the setting of the equipment is correct for treating a tumour in the side of the neck.
Field size 100, heart 80, and it's at 90. Okay. Nice and still, it'll be about 2 minutes.
They now leave the treatment area to go to the control desk. Operating the equipment removes the lead shielding and irradiates the diseased cells of the tumour.
2 minutes. Okay, 2 minutes.
When the cells are killed, the tumour will disappear. So even the dangerous properties of radiation can be turned to advantage. The discovery of X-rays and radioactivity led to a revolution in science, the atomic age. But for most people, it's the medical and industrial uses that have made the greatest impact.